Hi everyone. First, let me introduce myself. My name is Shivam Durgapal and I am a student of MSc Physics 4th Sem. In this video, I am going to talk about Van Allen radiation belts and space weather effects in it. My talk is divided into 7 parts. I will start with introduction first, then I will talk about solar terrestrial environment. Next, we will study the method we use for data analysis. Next, we will look over various geomagnetic indices. Next, we will discuss the various outcomes and then the results, and finally the summary and future possibilities. The discovery of the Earth's Van Allen radiation belts by instrument flown on Explorer 1 in 1958 was the first major discovery of the space age. The Van Allen radiation belt is a zone of energetic charged particles, most of which originate from the solar wind, that are captured by and held around the Earth by its magnetic field. The Earth has two such belts, and sometimes other may be temporarily created. The inner radiation belt consists of highly energetic protons and is located close to the Earth, ranging from about 1.2 to 2 Earth radii, and is stable. The outer radiation belt consists primarily of highly energetic electrons and is located from about 3 to 7 Earth radii and is highly variable. The shape of the radiation belt is distorted since the Earth's magnetic field is not a dipole field. The inner radiation belt is located closest to the Earth above the South Atlantic anomaly. The South Atlantic anomaly is the region where Earth's magnetic field is weaker than at other longitudes. Figure shows the cross-section of Van Allen radiation belts. The inner radiation belt is shown with red color and the outer radiation belt is shown with gray color. The belts are found in the inner region of the Earth's magnetosphere. In this visualization, the radiation belts with rainbow color and plasma pods with blue-green surface surround the Earth. Its structure largely determined by Earth's dipole magnetic field. The radiation belt is sliced open, simultaneously revealing representative confined charge particles spiraling around the magnetic field structure. Yellow particles represent negative charged electrons, blue particles represent positive charged ions. The question comes to our mind, why study the radiation belts? The answer to this is modern human society relies considerably on satellite technology, which provides essential services like communication, internet, GPS, and the timing signal for the stock markets. Unfortunately, most satellites operate in a region of space with a high risk of natural hazard, namely the Van Allen radiation belts. In this region, the concentration and energies of protons and electrons can reach levels that can damage the electronic components on a satellite by causing internal or surface charging, leading to deterioration which will cause interruption of services and in exceptional cases a total loss of the satellite. It is therefore imperative to be able to forecast the temporal and spatial variability of the condition in the near Earth environment, which are the fundamental principles of space weather research. Understanding the radiation belt environment and its variability is important for two reasons. First, it advances fundamental physics knowledge about space processes, and second, it will allow mitigation of space weather research in areas of spacecraft design and operation, mission planning, and astronaut safety. In the solar terrestrial environment, we will study the Sun and interplanetary space, the Earth's magnetic field, the Earth's magnetosphere, the Earth's plasmasphere, geomagnetic storms, and substorms. The environment of the Sun and the Earth form a coupled system that is linked through dynamic electromagnetic effects and charged particle interaction, which drive the space weather effects found at the Earth. The Sun is nearly perfect spherical ball of hot plasma, composed primarily of hydrogen and helium, with trace amounts of heavier elements such as oxygen, carbon, and iron. The Sun is divided into several layers separated by their density and temperature. From the outer layer called the corona, there is a continuous outflow expanding radially through the solar system. This so-called solar wind is a plasma primarily composed of protons and electrons whose energy is high enough to escape the sun's gravity. In addition to the constant flow of solar wind, there are the so-called coronal mass ejection, which are a release of large quantities of coronal matter into space, usually accompanied by electromagnetic radiation. The Earth's magnetic field, also known as the geomagnetic field, is believed to be generated by electric current in the conductive material of the Earth's core. If the Earth was isolated in space, its field could be approximated as a dipole field that is tilted away from the Earth's rotational axis by about 11.5 degree. The rotational axis itself is tilted about 23.5 degree from the vertical to the Sun's ecliptic plane. One particular feature of the Earth's magnetic field is the so-called South Atlantic anomaly, where the Earth's magnetic field is much weaker than at other longitudes, with consequences for the shape of the Van Allen radiation belts. The Earth's magnetosphere is the region of space where the Earth's magnetic field is able to control the movement of charged particles. On the day side, the Earth's magnetic field is compressed by the Sun's solar wind. The solar wind is diverted by the Earth's magnetic field flowing around the Earth and thereby extending the magnetic field on the night side. This so-called magnetotail can extend up to several hundred Earth radii and is comprised of two lobes, the northern and the southern lobe, which are separated by an area of weaker magnetic fields. Where the density of charged particles is higher, the so-called plasma seat. The region where the pressure from the solar wind is balanced by the pressure created from the Earth's magnetic field is called the magnetopause. One important part of the magnetosphere is the so-called plasma sphere, the region that contains a larger concentration of low-energy charged particles. The plasma sphere is mainly composed of hydrogen, helium, and oxygen ions, which form a cold, dense plasma co-rotating with the Earth. The source of the plasma in the plasma sphere is mainly the continuous outflow of ions streaming upward from the Earth's ionosphere along the Earth's magnetic field. A geomagnetic storm is caused by a prolonged coupling between the solar wind and the magnetosphere, during which large amounts of energy are transferred into the magnetosphere. In contrast to the long-lasting geomagnetic storms, substorms are short disturbances of the geomagnetic field, lasting for a few hours, during which energy is transferred into the magnetotail and eventually quickly released into the high-latitude ionosphere. Substorms are hence primarily observed in the polar regions, and they are accompanied by enhanced aurora. During geomagnetic storms and substorms, electrons and ions are injected into the magnetosphere. This animation shows a magnetospheric substorm during which the reconnection causes energy to be rapidly released along the field lines, causing the auroras to brighten. Since the geomagnetic conditions have a great impact on the shape of the Earth's magnetic field and hence the resulting particle distributions inside the Van Allen radiation belts, it is imperative to have a measure of substorm activity. Measuring the various corresponding parameters directly in space requires satellite to be present. Since these are unable to provide measurements at many locations in space at all times, we must rely on ground-based measurements. There are a variety of indices available that aim to provide measurements that represent the geomagnetic conditions based on data from a worldwide distribution of observatories. In the following, the most commonly used indices will be discussed. At first, we will discuss the auroral electrojet index. The AE index provides a measurement of the auroral zone component of the electric currents, which are often diverted along field lines during magnetic storms, in particular during substorms. Next comes the K-index. The K-index is used to quantify disturbances in the horizontal component of the geomagnetic field during irregular and rapid storm time magnetic activity. In the next, we will discuss the DST index. The DST index was designed to measure the enhancement of the westward magnetospheric equatorial link current due to injection of magnetotail protons and electrons. In order to study the space weather effects in the near-Earth environment, we will be using a method called superposed epoch analysis, which is a statistical tool used in data analysis either to detect periodicity within time sequence or to reveal a correlation usually between two data sequences. Using this method, DST, KP, AE and CRI are studied for a 24-hour interval. In order to understand how these indices respond to interplanetary sources during the starting phase of the solar cycle, one-day averages were studied for the year 2009 to 2014. The occurrence of geomagnetic storms are used as a 0 days with criteria DST less than equals to -50 nanotesla. We investigated the association of cosmic ray intensity with DST. It is found that CRI is found to decrease in similar pattern to DST for most of the period of the starting phase of solar cycle 24, apart from the year 2009 as shown in figure. CRI shows an exceptional behavior in 2009 with DST index. The strongest increment in CRI for 2009 takes place on the occurrence day of geomagnetic storm. From the figure, it is clear that the strongest decrement in CRI takes place on the occurrence day of geomagnetic storm, except for the year 2013 and 2014. The given plot shows the conclusion of superposed epoch analysis from -6 to +6 days with respect to 0 epoch day average for the year 2009 to 2014 for CRI and DST. The Kp index is used to quantify disturbances in the horizontal component of the geomagnetic field during irregular and rapid storm time magnetic activity. Figure shows the variation of Kp with DST by using superposed epoch analysis. The study of correlation coefficient during geomagnetic storm period shows that Kp and DST are anti-correlated. The strongest increment in Kp takes place on the occurrence day of geomagnetic storm for all the years included in our study. The correlation coefficient averaged for the years 2009 to 2014 was found to be -0.89, which shows a good anti-correlation between Kp and DST index. Here the plot shows the conclusion of superposed epoch analysis from -6 to +6 days with respect to 0 epoch day average for the starting phase of the solar cycle 24 for Kp and DST. The AE index provides a measurement of the auroral zone component of electric currents which are often diverted along field lines during magnetic storms, in particular during substorms. Figure shows the conclusion of superposed epoch analysis from -6 to +6 days with respect to 0 epoch day for the variation of AE and DST. It is clear from the figure that AE and DST are well anticorrelated with one another. The strongest increment in AE takes place on the occurrence day of geomagnetic storm for all the years included in our study. The correlation coefficient average for the years 2009 to 2014 was found to be -0.88, which shows a good anticorrelation between Kp and DST. The given plot shows the variation of Kp and DST averaged over the starting phase of the solar cycle 24 using superposed epoch analysis from -6 to +6 days with respect to the 0 epoch day. The study of yearly averages reveals that the annual average of AE for 2012 is the greatest. This indicates a greater intensity of auroral electrojets in 2012. 2012 is also characterized by greater average value of DST and shows higher intensities in the ring current and consequently a higher occurrence of geomagnetic storms. The average of Kp is higher for the year 2012 following the trend of AE to which it is in general better correlated. The yearly average of CRI is found to be greatest for the year 2009, that is at the minimum of the solar cycle. The study reveals that the correlation coefficient of Kp and AE is in general the highest. Year 2009 shows an exceptional behavior by having a negative correlation between DST and CRI. Highest correlation between DST and Kp was found for the year 2009 and it shows highest correlation for DST and AE. The maximum correlation between DST and CRI was found for the year 2010. KP and AE has highest correlation for the year 2012. The Earth's radiation belts were the first great discovery of the space age. With the realization that near-Earth space was filled with very energetic particles, there was a recognition of the deleterious effects that could be produced in spacecraft and biological systems flying in space. The space weather impacts of the radiation belts have only increased over the past decades as humans have used space more and more intensively for communication, navigation, weather forecasting, and countless other applications. Deeper physical understanding of the radiation belts and their temporal variation has become a pressing requirement in the space age. In this, we reviewed the structure and dynamics of the radiation belts from the scientific perspective. In this work, an effort has been made to achieve a better understanding of the geomagnetic indices and their relationships during the starting phase of the solar cycle 24 by means of their averages and their correlations. As described, the radiation belts are an integral part of the overall magnetospheric environment of Earth. As such, the Van Allen belts are intimately coupled to the ring current, plasma sphere, ionosphere, and magnetotail regions of our planet. More or less from the discovery of the radiation belts, it was recognized that intense population of penetrating particles could be highly damaging to electronic systems in space as well as to spacecraft, structural material, and spacefaring human beings. Quite importantly, there is ample evolving evidence that the loss of radiation belt particles into the Earth's atmosphere can have profound effects on the chemistry and electrodynamic state of our planet. This means that the coupling from the radiation belts into the mesosphere and stratosphere must be actively considered as contributing to the richly varying properties of the overall atmospheric system. This fact amplifies the importance of studying and monitoring the state of Earth's radiation belts now and in the future. Thank you.